He's going to talk to us about forest and trees and nature.
Right, thank you very much. My name is Michael Kay. It's not my first time here, but that doesn't mean everyone knows me. I created and founded the Saxonica company. I write XSLT processors for a living, and XQuery as well. And welcome to the club, Zachary. It's great fun doing it. It's even better if you can get people to buy your beer. So, coming back to tree models. Tree models, I learned very early on in this process that getting the right tree model has an enormous effect on what you can do with XML processing. And I've been revisiting the area recently to see whether we can get even better at what we do with the tree models internally. So I'm going to start with a series of somewhat disconnected observations, which I hope will pull together as we go along. And the first one, which might seem to have nothing to do with tree models, is that a compiler should be written in its own language. And that is particularly true for an XSLT compiler. Why is it particularly true for XSLT? Because what do compilers do? If you look at the textbooks on compilers, what they do is they transform trees into other trees. They run through a series of phases, basically taking syntax trees and adding semantics and doing type checking. And all those phases are really tree-to-tree transformations. And if XSLT is designed for transforming trees into other trees, then if it can't do compilation, then there's something wrong with it. So it's a good test as to whether we've got the language right, and it's also it should be applying the right technology to the job, since it's a tree transformation task, and we've got a tree transformation technology. Now, if you're not used to the idea of writing a compiler in its own language, it might be a little bit mind-boggling. How do you do it? How do you ever get started? How do you compile the compiler if you haven't got a compiler to compile it with? The answer is you need another compiler to compile it with, and we're fortunate in Saxonica in that we've already got one. So we've got an XSLT compiler written in Java, and so it's all fairly easy. You write an XSLT compiler in XSLT, you compile the XSLT compiler written in XSLT using the XSLT compiler written in Java. You end up with an executable, use that executable to compile the XSLT compiler written in XSLT to produce another executable, and it's all very easy, really. Once you get used to the idea, but don't try it at home. So what's the relevance of tree models? The relevance of tree models is that about 10 years ago, at Extreme Markup Languages, the predecessor to Balisage, I presented a paper about how to write an XSLT optimizer in XSLT, which is just one part of the compilation task. And I did some experiments, and I came to the conclusion that it was a nice idea, but it couldn't be done fast enough. And the main reason it couldn't be done fast enough is that optimization is a very incremental process. You want to keep transforming parts of little subtrees of your tree, and you want to do that incrementally and repetitively. And the problem is that the architecture of XSLT is such that the cost of making even very small changes to the tree is linear with the size of the tree. And that's a consequence of the tree models that we've got and the general architecture of the XDM data model and the way we manipulate it. So there's a basic issue that we have to solve, which is that XSLT transformations take at least linear time. The simplest transformation, even if you're just changing one attribute of one element, involves copying the rest of the tree. It involves a zero change to 99% of the tree costs you just as much as, costs you more than the one little change that's actually doing something useful. No, it's a consequence of a naive interpretation of all the way the data models are written and everything else. It's the intent of this talk to show that it's not a necessary consequence, but it's an inevitable property of a naive implementation of the specification. So, interesting observation, that doesn't apply to JSON trees, where by JSON tree I mean the way that we model JSON in XSLT and in XDM. We're using maps and arrays. They can be updated in constant time. Why is there that difference? And I mean, one thing I thought about in trying to write and I'll go back now to writing an XSLT compiler in XSLT, because we've actually been doing it. And in fact, just last week, we got as far as the critical milestone of actually being able to compile the compiler. So we've got that far. There's still a long way to go, but that's an important milestone. It means we can now start doing the development in XSLT rather than using the Java compiler to do it. And I thought we were going to have to do a lot of the data structures in using the JSON part of the data model rather than the XML part of the data model, simply to get round this problem of doing fast updates to parts of the tree. And I thought, you know, there's something wrong there. We really ought to be able to do this efficiently using the XML part of the model, because we've got so much richer functionality there. We ought to be able to deliver the same performance. Why can't we? So why is the difference? What's the difference between these two data models, that makes this true? Well, let's look at how we handle the updates on JSON trees. And so a little bit of a digression here into what are often called immutable trees, or some people call them persistent trees. Those words have lots of other meanings as well. I sometimes therefore call them version trees. It's not a spelling mistake on the slide. I'm told that these are pronounced trees, even though some people pronounce them tries to make a sort of pronunciation distinction. But it's a particular kind of tree. It's intended to combine the words tree and retrieval. Trees that are efficient for searching and information retrieval is why the term was invented, and it's confused everyone ever since. But a simple exposition of how they might work is not as simple as this, but you might imagine that if your keys are strings, then you can index a word like atom simply by having a succession of paths on the characters of that string, finally taking you down to the leaf value, which in this case is 1, 2, 3. So if you want to search for the value atom in that tree, then you take the letters one by one and work your way down the tree. Saxon actually uses hash trees, which means that you don't use the original character string, you use a hash of the character string, and then you work your way through the parts of the hash code to get down there, but it's much the same, except it's just one extra level of refinement. What happens when you modify one of these trees? What happens when you do something like this? Now, the essence of a functional language is that after doing that, you get a new tree bound to the variable $n, but $n still binds to the old tree. And what you want to achieve is that update can be done without copying the whole tree. The way that immutable trees achieve that is that you only change the nodes that are affected. So here we've done an update that changes mar to 39. So we need to change what A is, and because we've changed what A is, we need to change what M is. Because we've changed what M is, we need to change what the top level thing is. So we get a new top level node that points to a new second level node and a new third level node, but everything else is unchanged. So the new tree for $n reuses the vast bulk of $m. It's unchanged. 99%, the cost of making the change is proportional to the size of the change rather than to the size of the tree. So that's the way that works. How come it works for JSON? Why can't we use that same technique for XML? The difficulty is to do with node identity and document order, and in particular, owner pointers, parent pointers in the tree. These trees don't have any parent pointers. There's nothing that points upwards. if there was something that pointed upwards, then you'd have an ambiguity, because the unchanged branch of the tree would have to point to two different roots. And it can't do that. That's no problem, because in the XDM model for JSON, we can't navigate upwards. I gave a presentation here 2 years ago on transforming JSON using XSLT3, and I found it quite difficult because there are no constructs that enable you to discover context. You can't navigate upwards to your parents in a JSON tree. So in the tree, the updates are cheap because we don't have parent pointers. That enables us to share subtrees when we've done an update. The new tree can have common components with the old. And there's absolutely no intrinsic reason why XML trees and JSON trees should be different in that respect. If you looked at the grammar for XML and the grammar for JSON, there's nothing there that would tell you XML obviously has to have parent pointers, JSON obviously doesn't. And yet all the models that we have for XML always have parent pointers and upwards navigation. All the models we have for JSON don't. It's part of the culture and tradition. It's not a necessary technical consequence of the fact that the syntax or even the data models are different. So we can look at that from two perspectives. What can we do to improve the JSON model to give it some of the benefits that you get when you do have parent navigation? Or we can look at it from the perspective I'm taking today, which is what can we do to the XML model to get some of the benefits that you get in the JSON world when you don't have parent pointers. So it's quite useful to be able to get information from your parents. In the XML world, we often have context information on attributes that applies to a whole subtree. XML lang is a classic example of that. An XML lang attribute gives the language for everything underneath it within its subtree. Namespaces are another example. It's a common feature of the way we design XML structures that we have attributes that have scope and apply to everything below them. And so when you're doing processing, if you're writing template rules, your match patterns very often want to access the context in which an element appears rather than just that element and its subtree underneath it. And that's very much the problem I had when I was doing JSON transformations, that I wasn't able to access that context information to say I'm not just interested in processing a city, I'm interested in processing a city that appears part of the invoicing shipping address. Because that processing might be different from a city that appears somewhere else in the document. So the context information is useful for transformation. But the key point here is that to access that context information, you don't actually need parent pointers. Because the only way of getting to a node in the tree is by going down to it. And you don't need a pointer back up because you know where you came from. So the key here is remember where you came from, and then you don't need an explicit pointer to go back up. Remember how to retrace your steps. So here's a little tree that doesn't have parent pointers, just to illustrate it. We'll do a little bit of navigation down this tree. We'll start there. So what we do at the start is, rather than just taking the node as it exists in memory, we create a wrapper around that node. So I've drawn the wrapper in red. And then we navigate down a step to here. And we create a wrapper around that node. And the wrapper around that node contains a pointer, a parent pointer to the wrapper node that we came from. And then we go down another step. And we create another wrapper, and we go down another step, and we create another. And so what we've created is another tree of wrappers, which is a transient tree that exists only so long as we need it. And in that transient tree, the nodes have parent pointers, but in the in-memory tree, they don't. And by using that idea, you can now think about sharing a subtree. A subtree can be shared between two different trees, and when you reach a node like here, it has different identity, it has different parents, it has different siblings, depending on how you got to it. So we've shared the physical in-memory data structure, but we've still got all the navigation capabilities of XPath of finding parents. There's now a difference between the logical tree and the physical tree. And the idea is that we can now exploit this idea so that when we do a transformation of a tree and we need to copy things, that copy can be instantaneous because we just flick a pointer. We don't have to physically create a new copy of nodes in memory. And that's what I've experimented doing. And my first experiment to do this, which is described in the paper, is a thing called a KL tree. Why K and L? Because they seem to be letters in the alphabet that weren't heavily used for other things. And one of them has a particular affinity. So I call the blue nodes K nodes and the red ones L nodes. And my first implementation of this was a simple link tree where the K nodes have pointers down to their children, and the navigation downwards wraps them in an L node, which contains two extra bits of information. One is the sibling position, the count of preceding siblings, and the other is the parent pointer to the parent L node. And you find that if you've got those two bits of information, you can do all the things you need to do, like sorting into document order and finding your way back up the tree and using the more complicated axes like following and proceeding and the even more complicated things which I haven't quite implemented yet, like getting the base URI right and that sort of nonsense that you have to do in the XML world. And the bottom line was that was fast, but it wasn't fast enough. In Saxon terms, it was faster than using DOM, it was faster than using JDOM, it was as fast as using the link tree, but it wasn't as fast as Saxon's tiny tree. It was about 3 times slower. It's easy to be faster than DOM. It's not easy to be faster than the Saxon tiny tree. And that's a problem in terms of actually integrating this technology, because it's all very well doing one thing really well, which is a very fast, deep copy. But if the other more common things you need to do, like navigating downwards using a simple path expression, take 3 times as long, then that's a bad deal. Now, it'd be nice if we could distinguish the cases where this tree is the one to use versus using a tiny tree, but we can't. And having a user configuration option is a waste of time. If only 10% of style sheets are going to go faster with this model, and if only 10% of your users know that the model exists, then you've actually only given a 1% benefit to the user community, and no one's going to buy you pints of beer for that. So nice, but not good enough. So the next thing to do is to try the idea on the Saxon tiny tree. I'll do another slide that shows a bit more what the tiny tree looks like. The key thing about the tiny tree is it doesn't use Java objects as nodes. It's essentially a tabular data structure, and it's a tabular structure in which each column is a Java array. So there's an array holding the depth of the node, there's an array holding the node kind, there's another holding the name, which is coded as a number which you look up in the name pool. And what happens when you do a path expression /a/b/c is that these arrays get searched. And it's just looking for a node kind 1 with a name of 2, 3, 4, 5, and it's 2 integer comparisons. Or if you're doing a descendant search, then it keeps scanning until it gets to another node that's the same level as the one you started, and then it knows it's finished. So you end up with an incredibly tight loop to do those searches. You know, it ends up being about 6 Java bytecode instructions in the inner loop, which is just amazingly faster than anything else you can dream up. You know, it's an order of magnitude faster than searching a DOM. The problem is, from this point of view, it relies on physical adjacency. It's using arrays. So every descendant node has its own entry in this table, and therefore having a shared copy doesn't fit well into that scheme of things. But I found we can do it. And the way we do it is we introduce something into the array that's called an external reference node. It's like an entity reference at the lexical level. It just says, at this point, go somewhere else. And if you hit one of those nodes when you're searching the tree, then you have to go and search something else, which lengthens your inner loop from 6 instructions to 8. But it's not the end of the world. And in any case, you can only do it for those trees where this situation has occurred. So that can be made to work. I'm still dealing with the edge cases like base URIs and so on. But by and large, it is working. I've got the complicated things like sorting into document order working and so on. And there are some performance numbers in the paper which show that it's capable of delivering good results. The next challenge is, how do we take advantage of it? So where can we actually take advantage of cheap subtree copying? Well, the first obvious candidate is if the source code actually uses XSL copyof, then we're in luck. XSL copyof becomes very much cheaper. Actually, quite often the optimizer already eliminates the copying involved by XSL copyof, because we can see that it's the copying is unnecessary. It can just well, it depends what you're copying. I won't go into that detail, but there are a lot of cases where you don't actually need to do that physical copy already. But in the cases where you do currently do the copy, it can now be eliminated. Similarly, in XQuery, the equivalent construct, it has exactly the same semantics as the XSL copyof, is that notation where you use the curly braces instead of the copyof instruction. In XQuery update, the transform expression, or the copy modify expression, transform is new syntax in what was proposed as the XQuery 3.0 update draft, but has sadly been abandoned. But it's much nicer syntax than the old one, so I think I'll implement it anyway. Is this transform expression. It's still a purely functional effect. The effect of a transform expression has no side effects, but internally it's a sort of in situ language model for saying delete these nodes, and when you come out of the transform expression, you've got a copy of the original in which those deletes have been applied. I can see how to use that kind of construct with a fast copy, basically because at the end of doing those update expressions, you get a list of nodes that are affected by the updates. And if you've got a list of nodes affected by the updates, you can find all their ancestors. And then basically something that isn't on that list of affected nodes is going to be copied unchanged. And so as you apply the updates, you can simply say, I can do a fast copy on the parts of the tree that aren't affected by any of the update instructions. Rather more challenging is your typical XSLT way of doing a transformation, which is to use the shallow copy identity template model. In XSLT3, you can say that on XSL mode. In earlier releases, you write out the built-in template by hand that says, if I haven't got anything else to do with this node, then copy it and then recurse. It's rather more challenging to see how to translate that into a fast, deep copy, because you don't know whether any nodes in the subtree are going to have specific rules that do something different. But I think I can see ways, in some cases, if you've got a schema, and I wish more people would use schema-aware transformations, because there are lots of good optimizations you can do if you know the schema, then certainly that would give benefits. Even if you don't have a schema, I think there are a lot of cases where you can look at the subtree to see whether anything's changing and then copy it and still get a benefit. the other possible thing is, let's, why not consider doing an XSLT update extension? Just taking the XQuery syntax and mapping it back to XSLT. And that might be quite a nice thing to have as an extension to the language. The language was designed to be extensible. Why not use the fact? Now that we no longer have a W3C working group developing new features in the language, perhaps we need to, users and implementers need to take control and invent things themselves. So that's another possibility. With those things implemented, firstly, key message, and thanks, Stephen, for spotting it before I got there. The key message is, you might think the semantics of the language require parent pointers. They don't. All the existing tree models that we know about have parent pointers. It makes life easy, but it's not necessary, and it does have a disadvantage. If you don't have parent pointers, then copying subtrees becomes much cheaper. In fact, it becomes instantaneous. And if subtree copying is cheap, then in principle, small changes can be made in constant time. And that enables us to write an XSLT compiler and XSLT. Enormous conceptual leap there, but that's where we came from. That's how we got to this. And there's some performance numbers in the paper if you care to look at it. There's also some grotty poetry. Thank you.
So we have time for 1 or 2 questions. Yes.
So copying subtrees is cheap. Is that constant time?
Yes, you just flick a pointer.
So changing, won't that be log n time?
Log n time in terms of the total tree transformation, yes, but the actual copy part of it is instantaneous.
Oh, okay, yeah.
Yes.
Yeah.
When it will be possible to use, to try? I mean, when
I'm sorry, I didn't catch it.
When it will be released, when it will be available to try, to test, to play?
No promises. Next release.
Okay, thank you.
Sometime later this year, hopefully. Might scrap it all if it doesn't work.
Question? No? I didn't see. Oh, okay.
If you control your own input, you are able to choose your tree model. But in the Saxon.js case, you, I think, have to live with the tree model of the browser. Is that right?
Yeah, that's a very good question. In Saxon.js, we are currently using the DOM provided by the browser. And it's given us a lot of problems because, firstly, a lot of the optimizations we do to tree copying in the Java case don't work because in the JavaScript code, we're using entirely a pull model. So the semantics of what the product does are much closer to the semantics of the spec in that we do actually physically copy subtrees. And copying in DOM is a nightmare. And so that is definitely a performance bottleneck that we've got on the JavaScript side. And so that's another motivator for this that says we need to do better on the JavaScript side in terms of reducing the cost of copying operations. It's even more of a bottleneck on the JavaScript side than it is on the Java side. Whether that means we end up implementing our own tree model, and whether that tree model conforms to DOM or whether it's something closer to the tiny tree, open question. But you're quite right. Tree copying in our JavaScript code is definitely a bottleneck, and it's something it's another factor that has caused me to look hard at this area.
Okay.
Okay, thanks very much.
Thank you.